right, this presentation deals with simple harmonic motion in the terms of properties of waves and sound waves. And remember that you can always visit sciencewithmrnoon.com and you can see interactive videos, you can see presentations, PowerPoints, interactive labs that you can do, animations that allow you to do interactive stuff, and the online quizzes that help you test the knowledge that you might have obtained from these videos. So remember, just because you're watching this video doesn't mean you might not need to go to sciencewithmrnoon.com, unit on waves and sound, to learn about all the background information that goes with these problem-solving strategies. All right, so now that we got that out of the way, we will look at today's presentation. Simple harmonic motion. Simple harmonic motion occurs whenever an object oscillates between two positions for an indefinite length of time with no mechanical energy loss. We can observe this motion in a simple pendulum. All right, as I let this pendulum go, it continues to oscillate with little mechanical energy loss back and forth. So it returns just about to the same position each time during this cycle. Obviously, there's air friction, so a little energy is lost during this motion as it takes place. We can also observe this by examining the periodic motion of a mass attached to a spring. If this position right here is equilibrium, and I pull it past equilibrium and release it, we see this oscillation take place back and forth. All right? By examining this periodic motion, we can determine how a mass's velocity reaches maximum as the mass passes through the equilibrium position right in the middle and accelerates at maximum displacement from equilibrium. All right? It accelerates at its highest point, it begins to accelerate downward, and its lowest point from the spring, it begins to accelerate back upwards. So we have this maximum velocity towards the middle, and just like when we throw an object up in the air, when it reaches its highest point, it has a velocity of 0 as it begins to accelerate downward. And we also have an acceleration taking place upward as it reaches the lowest position in this mass on a spring. All right, so the time period is how much time it takes for one oscillation or one cycle. So if we have a pendulum bob and we have it so that it is in a circular motion, we could see that it takes to return to its original position in a circular motion is right where I release it. So if we consider this as a cycle and I release it from this point, it completes a cycle when it comes back to the point at which I released it. Now, completing one cycle, the amount of time it takes to complete one cycle, is known as the time period of this pendulum. Also, we see happening here in a spring, all right, if I release it from the lowest point, the amount of time it takes to go up and then return to the lowest point is the time period of one cycle. And it's commonly in seconds, even though it actually, the time period is measured in seconds per oscillation. It's referred to as just the amount of time per one oscillation for the time period. Now, frequency, on the other hand, measures the number of revolutions per second, which is known as hertz. All right, so we have frequency. It's the number of cycles per second. So if I take a stopwatch and I release this pendulum bob, as many cycles as it can complete during 1 second of time interval, then that would be the frequency, or how often this pendulum oscillates. It's the same, if this is one cycle, the up and down motion, how many times it can go through that cycle in 1 second is the frequency of our mass on a spring. All right, and we can see that there's an inverse relationship for seconds per oscillation and oscillations per second, or seconds per cycle and cycles per second. We have an inverse relationship between the time period and the frequency. So the time period is 1 over the frequency, and if you're looking for the frequency, you have 1 over the time period. All right, let's take a look at some objects in simple harmonic motion. We have here a mass in an equilibrium position on a frictionless floor attached to the wall by a spring. We can look at an object, let's go over here and look at an object in a similar scenario to this. All right, so here is a similar situation to what we're discussing on the presentation. We have a cart on an air track, and when the air track is on, we have a frictionless system going on. We have a spring that is in equilibrium position, and we can measure this spring, so 5 centimeters in equilibrium position. And if we compress the spring, then we will see that there is a measurable, now it's 4 centimeters, so it's been compressed by 1 centimeter. And if we extend the spring, we can find out from 5 centimeters what our stretching is, how much the displacement is from equilibrium position. All right, so as I turn this system on, I will compress the spring and let it go, and we will observe the motion of this cart in a frictionless system due to the energy that is in the spring force. All right, so we took a look at this system where we have a cart on an air track for a frictionless system and attached to a spring in equilibrium. And while it's in equilibrium, we could see that this distance is, our displacement is 0, because this is where our starting point is. Our reference point is a 0 position for displacement. And we also see that since it's in equilibrium, it's not moving back and forth, so the compression or expansion elasticity force is 0. As we move this cart away from the wall, expanding or stretching the spring, we obviously now have a displacement from equilibrium. All right, so this is the distance or displacement away from its starting position, and because we did that, we now have put in a displacement, maximum displacement, and we've put into a elastic force, which is commonly known as a restoring force. It acts opposite to the direction of displacement, so we displaced our cart this way. The restoring force wants to bring it back to equilibrium position. So our restoring force brings it back to the original position, equilibrium. And Robert Hooke determined that the amount of restoring force in an object divided by the displacement x that occurs produces a constant variable k, known as a spring constant. All right, so we have here the proportionality known as Hooke's law, and that is that your constant k is equal to your restoring force divided by your displacement. So if you look on your New York State Physics reference table, you will see on the back, under the mechanics section, you will see the equation that Fs is equal to Kx. Fs being the spring force, commonly known as a restoring force in a spring, or and K being a spring constant, and X being the displacement of the spring from equilibrium. We already previously looked at the restoring force and a displacement X and a spring constant K when we talked about work and energy. The amount of work done by a spring being the potential energy of elastic potential energy is our 1/2 K being the spring constant displacement squared. And we also saw this as determining the speed that is released of a spring into kinetic energy, 1/2 mv squared. So we could determine the period of a mass spring system. All objects that undergo simple harmonic motion, we could determine their period using the equation t, the time period, is equal to 2 times pi times the square root of the displacement of an object undergoing simple harmonic motion divided by the acceleration which takes place by that object. Using this equation to determine the period of a mass spring system, and knowing that Hooke's law is force equals Hooke's constant or spring constant times the displacement, and also knowing that Newton's second law is the force is equal to a mass times acceleration, we can now combine these equations so that we have a spring constant times the displacement is equal to a mass times an acceleration, and we have an acceleration is equal to a spring constant times displacement over the mass of the object. So if we take this acceleration and we replace A with kx over m, we see that we can rearrange this equation so that the time period of a mass spring system can be determined by by the mass divided by the spring constant, square rooting that, times 2 times pi. So when we have a system that's horizontal, or if we have a system that's also vertical, if we know what the spring constant is, then we can determine that the mass of the object, we can determine what the period of that object with that mass would be. All right, let's take a look at our first question here. A 5.5 kilogram cat is attached to a fixed horizontal spring of stiffness 22.8 newtons per meter and is set in motion on a frictionless surface. Find the period of motion of the cat. So we use our equation that the time period is equal to 2 times pi square root of the mass of the cat over the spring constant of the spring. Our spring constant is 22.8 newtons per meter, and the mass of the cat is 5.5 kilograms. And we put in pi, which is 3.14 times 2, and we determine that the period of oscillation back and forth for the cat would be 3.1 seconds. All right, so now what if we have a mouse, which is 240 grams, with the same spring and the same frictionless surface? What would the time period be for the mouse? All right, now remember, we have to convert grams to kilograms because it's the MKS systems, meters, kilograms, seconds. And we have 240 grams for this mouse. We convert it to 0.24 kilograms, whether you just simply move the decimal 3 spaces or go through your factor label method. We determine the time period is 2 times pi square root of mass divided by the spring constant K. And we determine that if we have the same spring with a 22.8 Newton per meter spring constant, and if we have a mass of 0.24 times 2 times pi, we get 0.64 second time period for one oscillation. So we have a much faster oscillation for a less massive object with the same spring constant. All right, what stiffness must the spring have so that the period of the mouse's motion is the same as the cat's. Right? If we were just to guess, then we would see that you would need a less stiff spring with a spring constant less than 22.8. But to specifically determine this, we need to use algebra to rearrange our equation to find time periods so that we can solve out for the spring constant K. The first thing you want to do is you want to divide this side by 2 pi, divide this side by 2 pi, and we got time period over 2 pi is equal to the square root of mass over spring constant.
Attention please, the 3-hour test period is over.
If we square this side, we square everything on this side, and we can see that t squared is equal to 2 squared 4 times pi squared is equal to mass over the spring constant. And now if we cross multiply, we can see that 4 pi squared times the mass is equal to the spring constant times the time period. And now if we just divide by the time period squared on both sides, we have our new equation that's solved out so that we can quickly find the spring constant. We plug in our numbers, mass of the mouse, and we want the time period for the cat, right? Right, we have the same mouse mass and cat's time period, and we solve that out and we get 0.99 Newton meters for the spring constant, Newtons time per meter for the spring constant. All right, we have a 1,275 kilogram car, carries 2 passengers with a combined mass of 153 kilograms. The car has 4 shock absorbers, each with a spring constant of 2 times 10 to the 4th Newton meters. Find the frequency of the vehicle's motion after it hits the pothole. So we're looking for frequency. A car, we're looking for shock absorbers that go up and down, and we have masses attached to these shock absorbers. And after it hits a pothole, they begin to oscillate with simple harmonic motion. We want to determine what the frequency of these masses are. So we put together our equation that we know now is to find the time period. We have 2 pi times the square root of mass over spring constant, but we also know that our frequency is equal to the inverse of time period, or 1 over the time period. So we have all of this placed in there. We put in our numbers, and we determine that the answer is 1.2 hertz, or oscillations per second.